All right, so the first thing I want to talk about for today is geometric isomers. It is very unlikely they will ask you a question to explain geometric isomers, but it does still come up in level 3 in the flow chart, which is why I want to cover it. So first thing I need you guys to just kind of keep in mind, these black balls, spheres, are carbon. Should have 1, 2, 3, 4 little places to put things in. The red is my oxygen, and the whites are hydrogen. Now, I've given you 2 different types of hydrogen. They're both the same in theory, but I've given you 2 different types because I want to make sure that it's very clear what we're dealing with. Okay. First thing I want you guys to do is take your oxygen, and I want you guys to stick one of the mushrooms on there. The hydrogens that have the little blob. And then we're going to stick one of these guys on as well. So it looks like that. So we are making an organic compound. Which organic compound is it? Or not an organic compound, a functional group. What functional group is this one? If it has oxygen and a hydrogen. HO, which is alcohol. So we're making 2 alcohols. All right? The next thing I have too many hydrogens, I think I might have given you guys 1 extra hydrogen that you didn't need. All right, that's okay. All right, then we have our 2 carbon atoms, and I want you guys to take the longer bendy one and put it together like that. So stick one of the longer bendy ones in there. Oh, wow, you're really not going in there. There we go. This is not the carbon that I want. Check to make sure you have 4 holes. Mine only had 2. Carbon 2. Not what I wanted.
Yeah, there's a different type.
Yeah, so if I want, you should have 4 holes in the carbon. If you don't, go back and grab one. There we go. But the idea is I should be putting 2 of those in there, like that. And then each carbon should have an alcohol. And it should also have a hydrogen. Now we're adding this hydrogen a little bit bigger because I just want you guys to see it as like 2 separate things, like that. Okay, so one of your carbons, so we're making a 2-carbon molecule, should have the OH, and it should have a hydrogen. And then the other one should be the same. I'll pull these ones out for now, like that.
Is this?
Yeah. Grab this to show my point. Right. Guys got it?
Okay.
So I just want you guys to make this. So, and then we'll put them together to make our double bond. All right? So currently, what I am starting to set up is an alkene. Let me start drawing it so you guys can see it. So I am starting to draw an alkene, so CC. And I'm drawing it so that way, or I'm creating it so that way it has an alcohol. And it looks like that. Okay? Are we good with that so far? All right, then I'm going to attach my double bonds. This one's also a duft one. Let me get you a different one. To it. Problem is, I really should have color coded those 2 different ones. All right. So, we're going to be making a double bond to put them together, like that, and like that, and like that. Looks like that. So that's what you should have designed. So we're making this molecule.
Why is one of them HO and the other OH?
Just how I was writing it. They're both HO. I was just writing weird. Okay?
Yeah.
Now, do we have that molecule made? So we have the hydrogens on the bottom, we have the alcohols on the top. Now, remember how when you guys were drawing organic molecules and you were asking me, does it matter if I put something on the top or on the bottom? And I said, it usually doesn't matter. In this case, it does matter because the double bond cannot rotate. So you see how I can't twist the molecule around? All right, and you can try to force yours to do as well. If this was a single bond and I had something else attached to it, say another hydrogen, so I'm going back to an alkane structure. It's actually still just an alcohol. So you see how in this case I broke the double bond? It now rotates. Yeah? So when you have a single bond, it can rotate. So it doesn't matter where you draw things orientation-wise. But when you get rid of two of them, and I attach them, make another double bond, it now does matter where they are arranged in space because it doesn't rotate. Do you see how in this case now when I've rearranged it and I broke and remade the bond, now my hydrogens are on opposite sides and my alcohols are on opposite sides as well. So we need to physically break the bonds in order to change it into, oh, that's going to snap, in order to change it. So that's my other option, where the OH is on separate sides. Are you okay with that so far? So these are what we refer to as geometric isomers. So both of these two have the exact same bonding pattern in a sense that the double bonds in the same place, the OHs are on the same place. Yeah? But the arrangement in space is different, so that's why we call them geometric. So these are on the same side, these are on opposite sides. And with the pre-learning you guys were doing, you learned that if they were on the same side, we call them cis. So this orientation is known as a cis. The way I like to remember is cis, same. You also hear, oh, cis, same. And then this one here, opposite side, so that's trans. That's that orientation. Now, one way to remember the bonding pattern is think about when we talk about gender identity. And you have, trans. So trans people, they are born with one gender, but they identify with a different one. Cis means that you are born in the same gender that you identify with. So that's one way to think about it. So cis, same, trans, different. Trans, you can also think about transfer. So I transfer from one side of the molecule to the other. All right? So I just have those as like little ways to help me remember which is which. This is very important because, like I said, when they are in that double bond, you cannot rotate them. And so we have to physically break them apart to make the bond that we want. Okay? So just be mindful. This doesn't really come up as something else to keep in mind is if you have this, that's not what I wanted. For a cis-trans isomer to occur, you need to have different things on each carbon. So if I have this arrangement here, this does not form geometric isomers. Because if it can't rotate, but if it does rotate, it's still the same molecule. You see what I mean? So it's something else to keep in mind. You need to have different things on the carbons involved in the double bond. Okay? So for example, if I had a structural isomer of this, like that one doesn't form cis-trans isomers. Now this one here is a structural isomer of this one. Are we good so far? All right. Just be mindful it might come up in the naming. It also might come up in the flow chart. So if I was going to name this, oh, never mind, that's time. We'll finish this up tomorrow. All right, can you guys take apart your molly molds and put them back in the boxes that correspond with the colors and the pieces? I'm hoping it's pretty self-explanatory. But does that make sense, cis and trans isomers? Yeah, I figured it was worth getting the molly molds out for that.